This unit is very short, just so you know. It's 2 days, because this is like extra material at the end of Chapter 5 that we just couldn't, it got to be too much, so we separated it. So we'll do 2 days. You're going to have one problem like what we do today, one problem like what we do tomorrow with what's called Simpson's rule, and then Monday I'll hit the highlights again, and you'll take a 2-question quiz slash test, and then we'll move on to Chapter 6. Simpson's rule is tomorrow. You know, the Simpsons show actually has a lot of, there's a writer that has a good mathematical, ooh, I better decrease that by 1 because it's already up to a minute. Yeah, the Simpsons program actually has a writer on there who has a very good mathematical background, and if I can find, there's a reference to Simpson's rule or something, I don't remember. I have something about the Simpsons and a math deal that's involved in their show, but I'll try to find it. Today is just application type problems. We've got a spaceship that's fired into orbit, and as the last stage of the booster rocket is fired, the spaceship is going 3,000 feet per second, which is a bit under 2,000 miles per hour. It's going pretty slow. Ha. Its velocity v of t at t seconds since the booster was fired is given by your equation here, 3,000 plus 18t to the 1.4, and they've got a graph on it. Now it says on the graph, pick a sample point t somewhere on the t-axis between 0 and 100. It doesn't matter where, guys. Just pick a point and label it t. Pick any point, anywhere between 0 and 100. Then it says show the corresponding point. So you want to go straight up from it to the curve, wherever your point's at. Go straight up, put a point up here, and label it t v of t. And that's all there is to number 1. It's not very difficult there. Then, on number 2, you're supposed to draw a narrow vertical strip of the region in such a way that this point is inside of the strip. So, actually, I may take this point off down here to give us room to label the dt, because we've got the point labeled up above. We're just going to take on either side of this point and draw. You can't get very narrow just because of, your pencil's fairly wide. But we're going to label this down here as dt. It's one little strip of the graph. Is everybody okay just getting that stuff labeled? That's not too difficult. And that's actually something you have to do on your quiz, believe it or not. You have to draw a strip and label it. So, next question. If the strip is narrow, i.e. dt is small, the velocity throughout the time interval dt is not much different from the velocity that you labeled, the v of t that we did on our point that we labeled. Explain why the distance traveled in this time interval is approximately equal to v of t times dt. Think about your strip there. If we want to find distance, that's going to be from velocity. Let me label this. Velocity, if we take the antiderivative of it, in other words, we go backwards, we get distance, right? So our distance is going to be the area under the curve off of that graph that we had on the last screen. You've got it there on the top of your notes page. So if I'm going to find the area under the curve for this strip right here, it's not quite a rectangle, but what they're getting at here is that we're going to take the height of it times the width. Well, the height of it, if I go, see if I kind of balance that out, the height of it is whatever I get when I plug my t back into the equation. So it'd be v of t. The width is what we labeled dt. And that just matches what they asked us to show. So that's good enough there. And while we're here, let's talk about labels. So velocity, the original equation, look back up in the first problem there. Velocity was it feet per second? Yeah, feet per second, 3,000 feet per second. So label-wise, we would have feet per second times your width is on the t-axis, which is time, and time is measured in seconds. Seconds cancel, and voila, we can also show it with labels, that when we do that we get feet. Questions there? Okay, the next part asks you to do a Riemann sum. Now, they want us to go from 0 to 100. And it doesn't tell us left, right, or middle. So we're going to do kind of a general equation here. Well, it doesn't tell us any of that. So we're going to do, remember the summation that we did for the integral? Yeah, it looks like a big capital funny looking E. So we're going to take our time from 0 to 100 there, and we're going to sum up. We don't know how many rectangles. We're not really doing a limit at this point. We're just summing up all these rectangles. And our rectangles from the last problem that we did could be found by taking the height times the width, or v of t times d of t. And really the only other thing that we could do there to this is we know what v of t is. Oops, not 0, 0, just 0. So we could plug in, what was that, a 3,000 plus 1 or 18t to the 1.4. So all I'm doing is replacing v of t with what they told us v of t was. So that is more of a general statement for any Riemann sum. We don't know how many rectangles. We don't know whether we're doing left, right, or midpoint, none of that. So we just write a general that we're going to be summing up a bunch of rectangles covering the time from 0 to 100 seconds. And here's our height, and here's our width. So that's all that's asking for. This is a summation. This means you're going to add up a bunch of rectangles. Any other questions on that one? That's all you're going to do on that one.